So we're coming to the, we've gone over the mechanisms of both types of reactions. We've seen the energy diagrams of both types of reactions. We've looked at intermediates, if any, that existed for either of the two. And methyl and primary alkyl halides will only undergo SN2 reactions. Tertiary will only undergo SN1. And secondary can be both. So when determining if it's SN1 or SN2, the most important factor is it methyl, primary, secondary, or tertiary? And when it comes to secondary, since it can be both, we have to look at some other factors. And these factors are basically the nucleophile, the leaving group, and the reaction conditions. So we started to talk about the nucleophile yesterday. So the nucleophiles or last class, the nucleophile is important because in an SN2 reaction, the nucleophile is part of the rate equation. It's part of the rate determining step. The nucleophile has to attack the electrophile. Whereas in an SN1 reaction, the rate determining step is the leaving group leaving to generate a carbocation. So there is no nucleophile in this rate equation. So if you've got a secondary alkyl halide and you use a strong nucleophile, you're going to increase the propensity of an SN2 reaction. If you use a really weak nucleophile, you're going to increase the propensity of an SN1 reaction. So whenever we're designing reactions, we are going to make them work the best way for what we want to do. If we want to do an SN2 reaction, we're going to use a strong nucleophile so we can do an SN2 reaction. If we want to do an SN1, we'd use a weak nucleophile so we can do an SN1. We wouldn't work at cross purposes, right? So depending upon what you'd want to do, you would use so if you want to do an SN2, you'd use a strong nucleophile. If you want to do an SN1, you would use a weak nucleophile. But that brought us to our question, what makes something a good nucleophile or a bad nucleophile? And we went over this steps that it basically followed, nucleophilicity typically followed basicity, and we'd already done all the basicity stuff at the start of the term. So this row, this is basically going right across the top row of the periodic table. Carbon is less stable with a negative charge than nitrogen, which is less stable than oxygen, which is less stable than fluorine. So this would be a better nucleophile. We just did this one previously. Negatively charged nucleophiles are stronger than neutral because, well, the conjugate acid, or if we think about it from a basicity point, the conjugate acid for this is neutral, conjugate acid for that is positively charged. The one thing which was different is that polarizable atoms are better nucleophiles. And so we looked at this equation where we've got a methyl bromide and we're using nucleophiles. And so when it's a methyl bromide here, it can only be an SN2 reaction. So this is a good measure, setting up this experiment like this is a good measure to determine what makes a good nucleophile. And so we see here that water is the slowest, followed by carboxylate anion, and then nitrogen, chlorine, oxygen, another oxygen here. But they notice that these ones, sulfur and iodine, are super nucleophiles, much, much, much stronger than these other ones along the first row. So nitrogen's a better nucleophile than oxygen when it's neutral because oxygen's more electronegative, less likely to donate its lone pairs. Nitrogen is, so it's less electronegative nitrogen, so it's more likely to donate these than oxygen is. Typical, that sort of stuff. So that was the general trends. And I think that's where basically we left off last class. Now, there are certain things that aren't nucleophiles at all. So remember, a nucleophile has to attack the nucleus. And if you have, like, if you're trying to be the nucleophile, like you're this oxygen, and you've got a bunch of bulky groups around you, your ability as the oxygen to attack a nucleus is going to go down because you've got all this steric, all these large groups that are getting in, which could get in the way. So there are certain anions that are really good bases because they can grab protons no problem. Remember, protons are tiny. So they're really strong bases, but they're terrible nucleophiles just based on the fact that they've got lots of steric hindrance. So potassium tertbutoxide is one of them. So it's basically deprotonate tertbutanol, and you've got tertbutoxide. This other guy here with these two isopropyl groups on the nitrogen, lithium diisopropylamine, LDA, these are really bulky isopropyl groups. And so this nitrogen is really, it's a powerful base, but it's a terrible nucleophile because it's just so bulky. And there are a couple of other ones which aren't charged. This guy here, DBU, it is a very good base, but it's a terrible nucleophile. And this actually, this takes us all the way back to, the first term sort of concepts. So DBU has got two nitrogens here. One is sp2 hybridized, one is sp3. And if we're looking at these two lone pairs, if this is going to grab a proton, is it these lone pairs which grab the proton, A, or is it these lone pairs here which grab the proton, B? One of them will, one of them won't. One of the lone pairs is delocalized, one of the lone pairs is localized. Remember, delocalized lone pairs are less likely to donate because they're too busy in resonance, right? So which of these two lone pairs would be the one which attack a proton? We've got a mixture of answers. It is indeed A, because these lone pairs here are localized. These ones here, these lone pairs are an allylic lone pair because they can be involved in resonance. And then the rest of the ring there. So it would be indeed A. Okay, good. So the key point here on this slide is that some species are really good at being bases, but they're terrible nucleophiles because there's steric bulk associated with them. So LDA and the tertbutoxide are the two most common ones we'll see in these courses. So they'll be used exclusively in reactions that you want to remove a proton, which will be the next chapter, the elimination reactions. Okay. So the key point here is that if you want to do SN1, you will choose a poor nucleophile. For SN2, you will choose a good nucleophile. And remember, when we're talking about these things, we're talking about in the case of secondary alkyl halides. Because tertiary can only do SN1, primary and methyl can only do SN2 at a rate which is measurable, so to speak. Okay, now the next thing we're going to talk about is the leaving group. And it turns out that the leaving group is important in both of the two reactions, because the leaving group is attached to Rx, right? So Rx is involved in both rate equations. It's involved for the SN1 and for the SN2. But we're going to talk about the leaving group because we want to actually see what makes a good leaving group and what makes a poor leaving group. And so the best leaving groups stabilize the negative charge. So what this means is that the best leaving groups are extremely weak bases. And so we've done all of this before in our acids and base section. So remember when we were talking about the conjugate base, if you have HA and it gets deprotonated, you make the conjugate base. Whatever was a really, really strong acid, if you had a strong acid, that meant that the conjugate base was exceedingly weak, and then that would be an excellent leaving group. So we will talk about that next. So they did a similar, some similar experiments. They take a nucleophile, and so this time they're changing the nucleophile. This time they're keeping the nucleophile the same, and they're changing the leaving group. And this is, of course, going to be an SN2 reaction here. This is SN2. And then they did this reaction. And what you see is that, so we want things that will stabilize a negative charge here. So we want this to be stable. And what do we see? I minus. Awesome leaving group. Br minus. Really good leaving group. Things like chlorine and fluorine were, chlorine certainly better than fluorine, but fluorine is not a good leaving group at all. And then other things with negative charges that we've seen, hydroxide, NH2, all these things are just terrible, terrible. Make that red, terrible. So they are awful leaving groups. And why is that? Because, well, oxygen stabilizes this negative charge because it's electronegative, but that's about it, right? So it's going to want to react. It's a very strong base. Remember, hydroxide is the strongest base there is in water. And the thing that these things have in common, as you get lower on the periodic table, the stability of that anion increases and its leaving group ability increases, right? So iodine, bromine are excellent leaving groups. It's funny because they're excellent nucleophiles too. So we can manipulate these to be both. But the key point here is that things like fluorine or fluoride, sorry, hydroxide, alkoxide, they are not leaving groups. And the thing which was the best leaving group, let's make this purple, was this thing, the OTOS. So what is this? So remember back when we were doing our acids and base chemistry section. Okay, it's the edge of the screen here. I'll draw it down. There we go. This functional group specifically Okay, we got an aromatic group here, but what's the other functional group in this molecule? Sulfonic acid, that is correct. So we have got, so remember, sulfonic acids were one of the strongest acids that there are. And why were they the strongest acids that they are? Because once you deprotonate them, so we got some base, you generated a conjugate base here. And this guy was stabilized by, there's a whole bunch of resonance structures where it's delocalized over all of these oxygens. So these were very stable anions, which made these like the most like powerful organic acids. Like they were down where HI is. Like they're super strong acids. So they are exceedingly stable anions, which would make these awesome leaving groups. And that's exactly what they are. So let's go back a slide here. And so this is the one we just talked about. So there are a number of different flavors of these the conjugate bases of sulfonic acids. If you've got a aromatic ring, these are called tosylates. So tosylate anion. If it's just a methyl group, it's a mesylate. And if the methyl group has got 3 fluorines attached to it, this is a triflate. And so the TF is just the abbreviation. It doesn't include the oxygen there. It's just so we've got, this would be a mesylate, MS, O-, TF, O-, TOS, O-. So these are all super, super, super awesome leaving groups. The triflate itself is the best, and because not only is it stabilized by all that resonance, but you've got these fluorines which would inductively stabilize that negative charge as well. So these are amazing leaving groups. Now, so OH is a terrible leaving group. The tosylates are some of the best. And this is important because this chapter is basically involving, we're talking about alkyl halides, doing substitution reactions with them. And if you've got a hydroxyl group, what we're going to see is that you can do SN1 reactions with these using acids, because we can protonate that OH group to convert it into a good leaving group. So if this, on my phone. Sorry about that. So oxygen's actually a good, water is a good leaving group, But hydroxide's a bad leaving group. So you couldn't just use a nucleophile and come in and attack and do this. That is definitely not allowed, because hydroxide is a bad leaving group. But what you can do is you can convert an alcohol into something that is a good leaving group, which would be which would be one of these sulfonic. This is a sulfonate. We can convert this into a sulfonate and then do an SN2 reaction on these, or you could even, yeah. Or you could technically do an SN1 reaction on these too. So there's a way of converting something which is a bad leaving group into something which is an awesome leaving group. So this chapter, which for substitution reactions, which is, we're talking about alkyl halides, it also works with these sulfonates here. So, and the way that the typical reaction conditions are to, if you wanted to convert this secondary alcohol into this secondary sulfonate, is using this species here. So you would use the mesyl chloride or the triflate chloride or the tosyl chloride. So it's bonded to a chlorine, which is, and then what you would need is a proton, is a base, like triethylamine, something like that. So if you've got your alcohol plus one of these chlorides plus triethylamine, this is going to generate the sulfonate. So, and then from there, you can use it in this SN1 or SN2 reactions. So, the hydroxide group itself is, so this is a terrible leaving group, but you can convert an alcohol into a sulfonate, which would make excellent leaving groups, depending upon which ones you wanted to use. The triflate's very expensive. In fact, it's not really the chloride which they use. It's something it's the anhydride of the triflate, which we'll talk about a bit later on in the next class. But if this is a methyl group or a aromatic ring, you would be the tosylate or the mesylate. So converted something which is a bad leaving group into something which is an excellent leaving group by these two reagents. And then this sulfonate can undergo the SN1 or SN2 reaction. They're typically used in SN2 reactions though. Right, so this part is basically just talking about, so hydroxide's a strong base, so this would be a terrible leaving group. Water is a very weak base, it's a weak base, so it would be a good leaving group. So the other way of, you can protonate these to make them into leaving groups as well. So there's two ways to convert an alcohol into a leaving group. One is just protonate it. That works typically quite well for SN1 reactions, or you can convert it into a sulfonate, and that'll work well in SN2 reactions. All right, so for leaving groups, we are going to use good ones: chlorine, bromine, iodine, or these sulfonates. Okay, so the last factor is basically the solvent, and the solvent really is super important. And so when I said earlier that if we want to do an SN2 reaction, we are going to use a good nucleophile. If we want to do an SN1 reaction, we are going to use a weak nucleophile. At the same time, we are going to use a solvent that is good for solvent. We are going to use a solvent that is good for SN2, or if in the case of an SN1, we're going to use a solvent that will be good for SN1 reactions. We wouldn't do an experiment in which you use a weak nucleophile and then use a solvent which would promote SN2, because that you're working at cross purposes there. So the solvent is going to be really important, and SN2 reactions have a solvent which is going to favor them, and SN1 reactions are going to have solvent types which favor them. And so we would always use the combination of solvent and the appropriate nucleophile if we wanted to do those two types of reactions. So, but when we're looking at solvents, there's basically three types for what we're going to look at: polar protic solvents, polar aprotic solvents, and non-polar solvents. And what do these mean? Okay, so the polar part is, does the solvent have a dipole moment? Yes or no? Yes, it is polar. No, it is non-polar. We sort of did that. We did that basically in at the very start of this term, or even in Gen Chem when we were doing our Vesper theory. You look at all the bonds in a molecule. Are they polarized? Yes, no. And if they are, is there a net dipole in any given direction? Let's talk about, where's my little. So for that, we basically need to know the electronegativity of the atoms in a bond, or we also need to know the molecular geometry if there's a net dipole. So this was all stuff that we sort of worked on earlier on this term. And so something like hexane, which is all carbons and hydrogens. So this is basically completely nonpolar, right? Because there's no polarized bonds in carbon and hydrogen have essentially got the same electronegativity. So this would be a nonpolar solvent. Water. So we've got lone pairs that are where basically that's an area of high electron density. We've got polarized oxygen-hydrogen bonds, so it's polarized in this direction. And overall, there's a net dipole for water, basically where I drew that first arrow. So it is a polar solvent. Now, a molecule can have polar bonds and be nonpolar, and carbon tetrachloride is a good example of this. So we've got carbon-chlorine bonds, but this is a tetrahedron. And all of these dipoles cancel out. So it is a nonpolar solvent, although there's polar bonds in it. So that's basically how we determine if something's polar or not. So if we've got something like, what would be some examples here? What would your guess be for this structure here? Would this be a polar molecule or would it be non-polar? This is a common solvent called THF. So it is functional group wise, it's a cyclic ether. Polar or non-polar? Yes, it is slightly polar, right? So it's basically a tetrahedron. We can draw this sort of like we drew the water. So it's going to have a slight dipole, basically in this direction. So it's a slightly polar molecule. It's okay. Let's think of another one. What about this molecule? We use it as basically to wash our dishes or take off our nail polish. Would this be a polar molecule? Yes, so this is polar. So we've got oxygen's more electronegative than carbon. So we've got, it's polarized basically in this direction. So it's got some polarity to it. Okay, good. Next one. Now, the next part though is, so there was polar versus non-polar. And the other part was if it was protic or not, protic. So protic versus aprotic solvents. This is a very simple sort of one here. Solvents capable of hydrogen bonding are what we call protic solvents. And so they're always going to have, well, the majority of them are going to have basically a hydroxyl group in them. So they're capable of hydrogen bonding anions. So if you've got an anion, X minus, for example, the delta plus side is going to be interacting with the hydrogen of the anion. So negative is attracted to positive type of thing. So protic solvents have protons that are attached to strongly electronegative atoms. The most common one is oxygen. Nitrogen, I suppose, has got some. If we're NH3 would be an example of a polar protic solvent. And so alcohols are, and water, I guess, are the two most common. Carboxylic acids too, I suppose, would be another polar protic solvent. So polar protic solvents, yeah, as I was trying to draw in the previous slide, they are capable of hydrogen bonding anions. So these little dots here, these little dots are meant to be, to say that this is hydrogen bonding to it. So it's capable of hydrogen bonding anions. And this is really, really super important because remember, nucleophiles are typically anions. And the ones that aren't anions have got lone pairs. So for example, water is a weak nucleophile. Remember, it's got some lone pairs that it wants to donate, right? And if it's got lone pairs it wants to donate to attack, it can hydrogen bond because just like these lone pairs are hydrogen bonding to other water molecules. So this is important because nucleophiles are anions and leaving groups are also anions. So the most common ones, water, alcohols, and carboxylic acids. Okay. So let's go back to, okay, so there's 3 classes. Okay, so there's 3 broad categories of solvents, right? The polar protic, the polar aprotic, and basic nonpolar. Okay, so the polar aprotic is the one we haven't talked about yet, and that's what this slide's about. So they don't contain polar bonds to hydrogen. So they weakly solvate anions. So back here on this previous slide, this anion is being solvated, right? So water is the solvent, and the anion is interacting with the water molecules to help dissolve it, right? So to solvate it. So, and because it's got a polar bond to H, this is a strong hydrogen bonding. Remember, hydrogen bonding is one of the strongest interactions there are. This is a really strong interaction. So if you've got sodium chloride, you can dissolve this really easily in water because the chlorine, the chloride, can be solvated by water. But if you take sodium chloride and you throw it into, say, if you got a jerry can of gasoline, which is basically made up of a whole bunch of hydrocarbons, it doesn't dissolve at all, right? Because this is a nonpolar solvent. Hexane or pentane or whatever it happens to be. So, and to dissolve something, you need to solvate both the cation and the anion. So for polar aprotic solvents, they don't contain polar bonds to H's, so they can solvate anions, but it is basically, it's a very weak interaction. So for example, here are some solvents that are polar, but there's no polar bond to H. So DMSO would be dimethyl sulfoxide. This bond here is very strongly polarized. DMF is another one where you've got a strong bond. Acetonitrile, this carbon's got a partial positive charge. This is and then HMPA, this guy's super toxic. It's not used very much anymore, but it's one of the most polar molecules or are polar solvents. But DMSO, DMF, acetonitrile, these are all very common solvents that are both polar and they don't contain any polar bonds to H, so they're aprotic. So there's a couple of things that, what we're going to see is that polar protic solvents, I'm giving this story away here, are going to favor SN1 reactions, and aprotic solvents are going to favor SN2. And we'll see why in the next couple slides. Okay, so if you've got some anion and it is surrounded by solvent, and you've got some alkyl halide here. Let's say it's a primary one. And as an anion, or the nucleophile, let's just draw it as a nucleophile, I suppose. So as the nucleophile, you want to come along and you want to attack so the leaving group can leave, right? But you're surrounded by solvent. And in every case, you will be surrounded by solvent because that's what you're dissolved in, right? Do you think, it all depends upon how well you are solvated by the solvent. So if this solvent is stuck to you strongly, so strongly solvated, or if you're weakly solvated, so the solvent's there, but it's not really glomming onto you too much, weakly solvated. So you can think of it as, okay, well, let's just ask the question first, chemistry term wise. Okay, so if you've got a bunch of solvent molecules stuck around you, is it going to be easier or harder for you to attack an alkyl halide? Right, it's going to be harder. So if the solvent molecules are attached to you really, really strongly, it's going to be harder for you to run off and attack some carbon. Whereas if there isn't really, the solvent's there, but it's not interacting with you in a strong fashion, you can basically run off and do what you want to do. I think of this as okay, let's pretend that you're out dancing at a nightclub and you see someone you want to dance with and they are surrounded by their friends dancing. Are you going to run up there and break into them and try to steal them away from whoever they're dancing with? Probably not. But if they're dancing by themselves, as Billy Idol would say, it would be a whole lot easier to, dance up beside them or do whatever. So in the case of, like, if you're surrounded by a bunch of solvent, if you're surrounded by a bunch of solvent, it's going to be hard to attack where you want to go. But if it's just very loosely, if you're loosely solvated by them, it's going to be easier. So hydrogen bonding, it does a couple of things. If it's strongly solvated, it's going to, if it's strongly solvated, it's going to reduce the nucleophilicity. Because you've got these things stuck to you and you got to get rid of them to before you can attack, right? But if you're loose, if the solvent molecules aren't really, they're there, but they're not paying any attention to you, well, then you can, it's a lot easier to run off and behave as a nucleophile and attack something. So we can basically depict this in an energy diagram, which is what what these words here are trying to say. So hydrogen bonding to a nucleophile does two things. It encumbers the nucleophile and it reduces the reactivity. So a bunch of solvent hanging around you really tightly, it can be harder to attack. The second point, though, is that because the solvent is surrounding you, it's actually making your ground state stability lower. So the next slide basically is trying to show this. So in a protic solvent, where if you're the nucleophile and you've got a negative charge here, and there's all of these water molecules solvating you, so you're hydrogen bonding with all these hydrogens. So it's harder to attack because you're hydrogen bonding, you're busy hydrogen bonding. But also, this actually lowers your energy. It's a stabilizing interaction. So this is stabilizing. And the unfortunate consequence of this is that what this means is that the activation energy for this reaction, the delta G dagger, this increases. It's stabilizing, so delta G dagger is bigger. Whereas if you're in an aprotic solvent, say DMSO. So in DMSO, the end, which is the delta positive, delta minus, delta plus, is the sulfur, right? And there isn't really much of a, like, if you want to do the intermolecular forces here, this isn't much. You got these methyl groups blocking it. This is a very weak interaction. Whereas with hydrogen, this is a strong interaction. So you're less stabilized. So in these cases with the protic solvents, I should have done this in a different color. You're way up here. You're a higher energy, which means that this delta G dagger, the activation energy, this means the delta G dagger is lower. So it's easier to get over that hump because you don't have to shed the solvent because this interaction's so weak. Whereas with water, this would be a strong interaction. So the nucleophiles in an aprotic solvent, they're higher on this energy diagram, whereas in a protic solvent, they're going to be lower. So it's all about the activation energy. So aprotic solvents are going to, the nucleophile is going to start up higher. So this is for SN2. Because remember, in an SN2 reaction, the rate equals some rate constant times the concentration of Rx plus the concentration of your nucleophile. So the rate determining step here, this nucleophile's got to get over this hump. And so in an SN2 reaction, it involves a nucleophile. So aprotic solvents are going to strongly favor SN2 reactions. And what we're going to see is that protic solvents do exactly the opposite. They're going to strongly favor SN1 reactions. And we'll see that next slide. I guess I should ask, does anybody have a question? Okay, I'll take that as a no. Okay, so now the next part, this is the nice, beautiful complementary part of this whole process, is that, okay, so in an SN1 reaction, the rate determining step is the leaving group leaves, right? So the leaving group departs. And then we're going to form a carbocation. So the other interesting part is that the leaving group is an anion, right? The best leaving groups are anions that can stabilize a negative charge. And so protic molecules can, like water, can interact with the X. And when this leaving group decides to take off, they are stabilizing it as they start to break this bond. So because there's a strong interaction between the anion and the solvent, the breaking of this bond can be stabilized. And so it's not like it's getting help to leave. So I guess there's a certain I'll just I shouldn't anyway. Okay, I apologize if anyone has recently broken up with someone and they're in emotional distress, but you can think of substitution reactions as a way of so for H. So let's pretend that you, I don't know, let's make this. Okay, so in an SN1 reaction, the leaving group leaves. So if you're in a relationship with, you can pack your bags and go. And that's one way that things happen, is that, okay, I'm leaving, this isn't healthy, bye, good luck in life, sort of stuff. And so people just break up and things happen, right? So you can think of this, so in an SN1 reaction, you can think of all these water molecules are your friends or family saying, oh yeah, it's probably a good thing, we'll support you, and we're gonna help break this bond. The other type of, in an SN2 reaction, is like, okay, I found someone better and bye. That would be a worse one, probably. So you were once in a relationship and then somebody new comes along, oh, boom, and now you are off by yourself, and this is now another thing. Anyway, so you can think of the solvent is basically helping the leaving group leave, because it can stabilize that anion as it's leaving, and it's basically stabilizing that transition state. So in an SN1 reaction, in a protic solvent, so this is Rx, this activation energy in the rate determining step, delta G dagger, is lower because the solvent helps break the Rx bond. So solvent can help basically break that or stabilize that transition state to break that Rx bond. Whereas in an aprotic solvent, they don't have, remember, in aprotic solvents, I think I drew it over here somewhere. This interaction here, this X, this, I'm trying to get my little laser here. This X, before I drawn it as a nucleophile, if this interaction with an aprotic solvent, this is a really weak interaction. So it's not going to help stabilize breaking of this Rx bond. So in an aprotic solvent, this delta G is way higher. So for SN1 reactions, you want protic solvents. And for SN2 reactions, you want aprotic solvents. So in protic solvents, it helps facilitate the breaking of the Rx bond to make a carbocation. So that's why it's going to promote an SN1. Whereas in aprotic solvents, they're very poor at solvating the nucleophile. So the nucleophile is higher in energy, so it can overcome that hump better. So it's two different processes for doing these sort of things. So right, so the question which was just asked privately was that these factors are important for secondary alkyl halides, because with tertiary, you can only do SN1, and with primary and methyl, you can only do SN2. And so if I want to do an SN1 reaction, which is on a tertiary carbon, I'm going to use a polar solvent, because I would be dumb to use a apolar solvent because it's just going to take too long, right? So when we're doing these reactions, we are going to see that the experimental setup, even with tertiary ones, we're still going to use polar solvents because it's just going to make the SN1 proceed quicker. And with methyl, excuse me, I got hiccups. And primary, we're going to use solvents that are still going to promote an SN2 just because it's going to be faster. So here are some examples of the solvent. So we've got an azide. Okay, we're a little bit past time, but this azide, and this is a primary alkyl halide, so it's best for SN2. And just look at the difference in the reaction rates with all these different solvents. So you wouldn't use methanol because it would just be too slow. Water, not much better. But once you start using these polar solvents, the rates really skyrocket. So it'd still be an SN2 reaction, but the rates would be faster. So why would you do it something which would take 2 days when you can do it and it'd take 2 hours? So you'd always set it up with something which is good. So the take-home thing for today is that aprotic solvents favor SN2, protic solvents favor SN1. And yeah. Is that our last slide? Right. Okay, so that's basically where we're going to end off. And so what we'll do at the start of next class, and the other thing I should say is that these polar aprotic solvents all tend to have, these aprotic solvents all tend to have acronyms like DMF, THF, DMSO. So these got HMPA. They basically all have acronyms. Those are basically polar aprotic solvents. Whereas alcohols, I would just draw ROH, right? It's easy just to draw the alcohol. Yes, I've got a question here. Will I be posting another assignment? Yes, I'll post another assignment, which is going to cover basically the last bit of this, the class stuff. So it's going to be it's going to cover the stuff we do at the end of term. It's going to almost be like a practice thing for the final. But the answer is yes. And is the final going to be more of this stuff, or? Yes, the final is basically going to focus mainly on stuff we've done towards the end of the term, but there will be the odd question, because as you will notice that most of the stuff here, what makes a good nucleophile, what makes a good leaving group, that's all goes back to our acids and base sort of things. So it all interrelates, but it will focus on the stuff towards the end of term. Substitution reactions. The next thing we're going to do is basically elimination reactions. We'll do that on, what day is it today? Today's Tuesday. We're going to do that on Thursday. Okay. 9:54. Sorry, I went 5 minutes late. Were there any other questions? It took, sorry, I posted the last, I guess I got behind in posting old lectures, but the last 3 are all in one file, which just went up, I think, well, yesterday evening. But I guess I'll see everybody on Thursday. If you have any questions, let me know and I'll try to answer them.
Thank you.
You bet.